Welcome back to the course of Applied Elasticity. In today's lecture, we are going to continue with our discussion on the bending of beams. We are considering the bending of beam problems under different types of loading. So, beams are one dimensional continuum which undergoes bending when it is subjected to bending moment, either bending moment or transverse shear load. So, we had already discussed 4 different types of bending of beam problems when the beam is subjected to either pure bending moment or concentrated shear load at one particular section, or uniformly distributed load over a span, or linearly varying distributed load over a span. Now, coming to the last type of loading which we are going to consider, here the beam is subjected to the transverse load with sinusoidal intensity. So, the transverse load expression Fx, this is written as some constant f, some sin beta x. If we are able to write the load, or if the load acting on the beam is equals to, if of this particular form, sin beta x times some intensity capital F, then we need to solve that problem using a different approach. So, that is what we are going to discuss now. All these previous 5 problems, here the stress function phi x comma y was chosen in the polynomial form. So, in one of the previous week's lecture, we had discussed that there are 2 possible form of stress function choice. One is called the polynomial form, another one is called Fourier form. So, in the xy coordinate rectangular Cartesian coordinate system, the polynomial form can be chosen as combination of different order or degree polynomial, second, third, fourth, fifth, all those we had used for solving this first 4 type of bending of beam problems. Now, coming to the last one, if the loading is not just a point load or uniformly distributed load or a linear function, if this is a trigonometric function, here it is a sin beta x, it may be cos beta x, sin h beta x or sin h beta x. If the trigonometric or hyperbolic functions are required to be used for defining the transverse loading, for such cases this polynomial form of solution will fail, and we must use or choose phi xy in the Fourier solution form. And for much more general type of loading, instead of a single sine wave, if it is any general periodic function of x, in that case the Fourier series solution is required to be used. So, however, we are going to consider a simple sinusoidal transverse load, for which the Fourier form of stress function phi xy we will be using. So, let us consider a simple supported beam like this of length L and total width 2d. So, the origin I had taken here, this is 0, 0, 0, origin at left edge face. So, y is varying between minus d to plus d, x is varying between 0 to L. It is subjected to sinusoidal transverse shear load on the top face in the downward direction, with qx being q naught sin pi x by L, where q naught is the sinusoidal load intensity. This is also defined per unit length. Q naught is having the unit of force per unit length. L is length, B is width, and 2d is depth, total thickness of the beam. Now, once the beam is subjected to this sinusoidal load intensity, for finding the reaction forces at both left hinge and right hinge, 2 simple support points, 2 hinge or pinned joints, we will be having the vertical reaction forces, which will be obtained by using the symmetry of the problem, also by using the vertical force balance. So, first is we need to find out total downward vertical force coming acting on the beam due to the sinusoidal load intensity Qx. That can be obtained by integrating this Qx over the entire length. So, Qx dx, Qx is downward shear load per unit length, if you integrate that dx from 0 to L, total span or total length of the beam, we will be getting total transverse load. It is added, a negative sign is added with that because the total transverse load is acting downward along the negative y axis. So, thus we are having the total downward transverse load as 2 q naught L by pi, which is integral q x dx 0 to L with a minus sign, and putting q x as q naught sin pi x by L, we will be getting the total transverse load acting on the beam as minus 2 q naught L by pi. Now, these would be supported by two reaction forces. Thus, reaction at both the ends, here at the left support and also at the right support, we will be having this reaction force R, and this R is equals to q naught L by pi, which is upward. So, total R coming 2 R from both the hinge will balance this transverse downward load acting on the top face. So, in the free body diagram of the beam, I have drawn R to be q naught L by pi upward at both the hinge points, and hinge or pin supports or simple supports are removed, and top face is acting with q x, the sinusoidal load intensity of q naught sin pi x by L in the downward direction defined per unit length of the beam. Now, let us try to write down the boundary conditions. So, starting with the left edge. So, left edge, this edge is x equals to 0 face, whereas right edge is x equals to L face. So, at x equals to 0, the left edge, there is no axial stress. So, sigma x x should be 0 for left free edge, no axial stress would be there. However, shear stress would be present on the left edge because of this R. This R is basically causing a shear stress distribution on the left edge, same for the right edge. So, similarly, the right edge is also free for any kind of normal traction. So, sigma x x L comma y is also 0 because right edge is defined as x equals to L plane. So, 1 and 2 defines the left and right faces being free of any kind of normal surface traction. Now, coming to the top face, the top face is defined with y equals to plus d, bottom face is defined with y equals to minus d. So, the normal stress on the top face sigma y is non-zero because of the sinusoidal load. So, sigma y for the top face x comma plus d is equals to minus of q naught by b sin pi x by L. This q naught by b term is coming due to match the dimension. Q naught is defined as force per unit length, sigma y is stress. So, we need to divide the q naught with the width of the beam at any particular section x, and thus q naught by b is the sinusoidal load intensity per unit area. So, sigma y on the top face y equals to plus d plane should be equals to minus q naught by b sin pi x by L, whereas for the bottom face, that being free of any kind of normal or shear, sigma y for the bottom face x comma minus d would be 0. So, these two are the normal surface traction on top and bottom face. Similarly, we can write the shear surface traction on the top and bottom face to be 0 because no shear is acting on the top, no shear force, external shear force is acting on the bottom. So, for both y equals to plus minus d, the shear surface traction would be 0. So, with these 5 on all 4 edges, we have defined the external surface traction. Mostly they are 0, only for the top face we are having sigma y to be non-zero, which is minus q naught by b sin pi x by L. Now, coming to the shear traction on the left edge. So, on the left edge, if you consider the left edge, there we are having this R q naught L by pi upward reaction force acting on the left edge. Now, considering any 2D stress element with this being positive x and this being positive y, the tau xy is positive on this positive x plane, and on the negative x plane downward tau xy is positive. Now, if you look at this left hand side plane, here tau xy should be downward by sign convention, whereas on the right hand side plane, that being a positive x plane, tau xy should be positive upward, that is along the positive y axis. So, for the left hand side, that is x equals to 0, left end face, boundary condition 6, integral b of this tau xy dy from minus d to plus d, that would give us the net downward reaction force, because by convention tau xy direction is downward here. So, b tau xy dy integral from minus d to plus d would be net downward reaction, but external load R acting is upward, that is q naught L by pi. So, as the directions are different, we are having this minus sign. So, for left edge x equals to 0, integral b tau xy dy from minus d to plus d equals to minus q naught L by pi. Similarly, we can write for the right end face x equals to L. Here tau xy upward is positive, which is in the same direction as R. So, then here there would be no negative sign, b tau xy dy integral from minus d to plus d is equals to q naught L by pi for the right end face shear force shear traction distribution at x equals to L face. And finally, due to absence of any axial loading at any x at any cross section, integral b sigma xx dy from minus d to plus d equals to 0, integral of the axial stress at any cross section over the total area is 0, as the problem is free of any kind of axial force along the x direction. So, these are the 8 boundary conditions available. Now, as I had already told, we are going to use the Fourier form of solution due to the presence of sinusoidal loading along x for the top edge y equals to d. We are going to choose our stress function in this form. If you try to recall the last week's lecture, where the general Fourier solution phi xy was written, which was having 5 set of terms. One is alpha 0 beta 0 term, which is a polynomial. Then that was followed by one term with sine beta x, one with cosine beta x, one with sine hyperbolic beta y, another was sine cosine hyperbolic beta y. Now, here the load, the transverse shear load is acting along the x axis on the top face, where it is function of some sine pi x by L type. So, as the sinusoidal loading is along x and that is represented by a sine trigonometric function, we are only considering the sine beta x term in the Fourier form of solution. If a cosine loading was acting on the top face, then the cosine beta x and the corresponding rip term should be used. So, based on the type of external loading present, you have to choose the proper form of Fourier or proper term in the Fourier form of stress function solution, with which the problem can be properly represented. Now, with this choice of stress function, if you substitute it in the boundary in the biharmonic equation del 4 phi equals to 0, you can see this is automatically satisfied. This is left as an exercise. You can substitute this form of phi here and verify that these particular Fourier form solution of stress function would automatically satisfy the biharmonic equation. That was already done while deriving the Fourier form solution. We had imposed this biharmonic condition for finding the form of Fourier form of stress function phi. Now, coming to the stress component, with this form of phi, if we obtain sigma xx, sigma yy and tau xy, we will be getting the 3 stresses like this. These 3 equations you will be getting for the 3 non-zero in plane stress components sigma xx, sigma yy, tau xy. Now, these 3 stresses or stress function involves 4 unknown constants a, b, c and d, which we need to obtain by using the boundary conditions. So, starting with the 5th boundary condition, tau xy or tau yx at top and bottom face is 0. So, tau xy x comma plus minus d equals to 0. So, I have written the general form of tau xy, replacing y with plus minus d and x remaining as x, setting that to 0. Now, as this cos beta x term was there in tau x y and these to be valid for all values of x with y equals to plus minus d, cos beta x cannot be 0. So, coefficient of this cos beta x, this entire thing at y equals to plus minus d should be 0. Now, you can see here we are having some terms which are even function of y, some terms which are odd function of y. These equation can be satisfied to 0, set to 0 for top and bottom face y equals to plus minus d only if both odd functions of y and even functions of y goes to 0 or vanish independently. So, how do you define this odd and even function? For example, sine hyperbolic, this is odd function, sine hyperbolic minus x is equals to minus of sine hyperbolic x. However, if you try that for cosine, cosine hyperbolic minus x is equals to cosine hyperbolic x. So, that is even function. So, all the even functions and odd functions of y should independently go to 0. Now, here you can see total 6 terms are there 1, 2, 3, 4, 5 and 6. Out of 6, if you carefully check, 3 terms are even and 3 terms are odd. If you look at the even terms, this cosine hyperbolic is even term. Then here you can see we have one more cosine hyperbolic, that is also even term, and if you look at this particular term d beta y sin h beta y, this total term, that is also even term, because sine hyperbolic beta y itself is odd term and that is multiplied with y. So, this is one odd function, y is another odd function, product of these two odd function will make the total function to be even. So, that is one even term. All 3 even terms added together should go to 0. Similarly, remaining term, this one and this one, these 3 are odd terms. So, summation of these 3 odd terms should go to 0 separately, and solving these 2 equations we can get a and b in terms of, express a and b in terms of d and c as a equals to minus d times beta d tan h beta d plus 1 and b equals to minus c times beta d cot h beta d plus 1. So, 2 of the constant we have replaced in terms of other 2 constants, and the c and d are yet to be solved. Now, so I have written those a and b expressions in terms of c and d. Now, we are replacing those a and b in the expression of sigma y. So, sigma y stress is now written as function of c and d only 2 unknown constants at this stage. Now, using the 4th boundary condition, sigma xx for the bottom edge x comma minus d is 0, bottom edge is free of any kind of surface fraction. So, these sigma y, if you substitute here with y equals to minus d and set it to 0, here you will be getting one equation relating c and d. So, here only d and c, 2 unknown constants were there. Setting sigma y to be 0 at y equals to minus d, we will be able to relate c and d in this particular fashion. Now, coming to the 3rd boundary condition, on the top face, the normal traction sigma y at x comma plus d would be equals to minus q naught by b sin pi x by L. So, here I am replacing sigma y as plus d, and then I am also replacing this c. So, this c whatever we got from this boundary condition 4, that I had replaced in the expression of sigma y, then sigma y is just function of d. After replacing c in terms of d, sigma y is now just function of d, only one unknown constant. So, you can see this right hand side is sigma y at x comma plus d, which contains only one constant, that is capital D, and this left hand side is q naught by b sin pi x by L. The minus sign I had cancelled from both the sides. Now, you can see this sin beta x term is the only x dependent part on right hand side, whereas on the left hand side the x dependent part is sin pi x by L. Now, left hand side constant is q naught by b, whereas right hand side constant is 2 beta square times this big expression capital D into this term within bracket, some numerator by denominator. This equation to be valid for all values of x, we must have this sin pi x by L to be sin beta x, or beta is equals to pi by L and D to be equals to this. So, the coefficient of sine term should be same and the function within the sine term pi x by L should be same as beta x, thus beta equals to pi by L, and putting that beta here as pi by L in all the terms in the expression of D, D would be coming out to be this, D equals to q naught cosine hyperbolic pi d by L divided by 2 b pi square by L square within bracket pi d by L minus sine hyperbolic pi d by L into cosine hyperbolic pi d by L. So, expressions are quite big. So, we are getting this expression of D. Now, as I had evaluated D in terms of external force q naught, now it is not just certain relation between the unknown constant, this D is completely evaluated in terms of external force q naught and other parameters like D and L, the geometry. Now, you can replace this D back in these three expressions of A, B, C, and with that and also using beta equals to pi by L, you can write the expression of rest 3 unknown constant C, A and B in terms of the externally applied sinusoidal load intensity q naught. So, this completes the solution. We had obtained this A, B, C, also D we had obtained first, and then using the interrelation between the A, B, C and D, we are getting all three other constant A, B, C in terms of the applied load intensity q naught, and those will be obtained like this. So, after obtaining these 4 constants A, B, C and D, now we will check the remaining boundary conditions. So, sigma xx is written here, the sigma xx form is written here. Now, if you look at the boundary condition 1 and 2, those are sigma xx at x equals to 0 and x equals to L, that is on both the faces the normal surface traction should vanish, sigma xx 0 comma y, sigma xx L comma y should be 0. Now, if you put x equals to 0 in this expression of sigma xx, sin beta x term will directly go to 0. Hence, for this x equals to 0, this particular term will go to 0, sigma xx is 0 as x goes to 0. Now, coming to x equals to L case, we know that beta is equals to pi by L. So, sin beta x at x equals to L is nothing but sine of beta L, which is equals to sine of pi, and once again that term is 0, sin beta x at x equals to L is sin pi, which is equals to 0, and hence this second term sigma xx at L comma y is 0. So, both of these two boundary conditions are directly satisfied with beta equals to pi by L. Coming to the next boundary condition, that is the case of 0 axial force, integral of b sigma xx dy from minus d to plus d is equals to 0. Now, replacing the form of sigma xx in this particular equation and performing this integral over dy from minus d to plus d, we will be getting this equation involving two constants b and c. Now, if we recall the relation between b and c, that was b equals to minus c times beta d cot hyperbolic beta d plus 1. Now, if you write this cot hyperbolic beta d as cosine hyperbolic beta d divided by sine hyperbolic beta d and simplify it, this equation would be c beta d cos hyperbolic beta d plus b plus c sine hyperbolic beta d equals to 0. Now, if I compare this particular case, this particular term is exactly same as the term present within this bracket of boundary condition 8. Hence, this term is equals to 0, that boundary condition of 0 axial force is also automatically satisfied. Now, coming to the last two remaining boundary conditions which are defined over tau xy, that is the vertical shear force at both left and right edge. So, tau xy expression is given here with beta being pi by L. At x equals to 0, at one of the edge, left edge, x equals to 0, this cos beta x term would go to 1. With x equals to 0, cot beta x is equals to 1. So, tau xy at x equals to 0 is given here. If you recall, the boundary condition 6 was this, that is the reaction force at the left edge, x equals to 0 edge. So, integral minus d to plus d b d tau xy at x equals to 0 dy equals to minus q naught L by pi. Now, tau xy at x equals to 0 we had already evaluated. I will substitute that here and then try to evaluate the left hand side integral and try to verify whether it is coming out to be minus q naught L by pi or not. So, if you replace tau xy at x equals to 0 on the left hand side integral and integrate this, it would come out to be minus 2 beta times within bracket capital D beta small d cosine h beta d plus a sin h beta d. Now, recall the relation between A and D. A was obtained to be minus capital D times within bracket beta small d tan hyperbolic beta d plus 1. So, replacing that A here in terms of capital D, this integral can be written as a function of capital D only, 2b capital D beta divided by cosine hyperbolic beta d within bracket this term, sin beta d cosine sin h beta d cosine h beta d minus beta d. Now, if you think about the expression of d we had obtained, the capital D, the constant, that was obtained like this, which was having a term in the numerator like this, which is almost same as this term with just a negative sign. Now, if I replace this in terms of capital D, so substituting these capital D expression here, this term would get cancelled with the numerator factor of capital D also. This cosine hyperbolic beta d term will also get cancelled, and with that the right hand side will be simplified to minus q naught by beta. Now, we know that beta is equals to pi by L for this problem. So, substituting beta with pi by L, this would be minus q naught L by pi. So, which was same as the actual right hand side given in the boundary condition 6. So, boundary condition 6 is also automatically satisfied with the obtained solution. And coming to the last one, that is boundary condition 7, at the right edge net vertical force is equals to q naught L by pi with a positive sign, integral b tau xy at x equals to L dy from minus d to plus d integral is q naught L by pi. This particular boundary condition is exactly same as the previous one, just two small differences. One is previous one was at left edge x equals to 0, this is at right edge x equals to L, and for the last case boundary condition 6, there was a minus sign on right hand side, here it is positive on right hand side, plus q naught L by pi. So, at x equals to L, if you replace and using this beta equals to pi L. So, this cos beta x would be cos of beta L, which would be cos of pi. So, that is minus 1, and if you replace that, these minus sign and that minus sign coming from cos pi will be cancelled. So, tau xy at x equals to L will be beta square multiplied with this big term within bracket. Now, replacing these here in the integral, it is exactly same as the previous one, just a minus sign is missing in the expression of tau. So, following a similar order of steps, writing A in terms of d first and then finally putting the explicit expression of d in terms of q naught, you can obtain this left hand side integral b tau xy at x equals to L dy from minus d to plus d as q naught by beta, replacing beta as pi by L, we will be getting q naught L by pi. So, with this the present Fourier form of solution satisfies all the boundary conditions exactly, and these state of stress which is expressed by these 4 constants A, B, C, D, that is valid for the regions remotely located from the two ends of the simple supported beam. So, apart from those two edges, the whatever stress field we got, that is going to give us the exact stress distribution using the Saint-Venant's principle for this particular Fourier form of solution. So, in this particular lecture we had talked about the simple supported beam subjected to sinusoidal loading, and instead of polynomial form of solution we had used the Fourier form of solution. Using that we had obtained the stress distribution, we got the expression of sigma xx bending stress, sigma yy and transverse shear stress tau xy using the Fourier form of stress function. Thank you.